tell us more about.
Thanks, Tiak. So thank you all for coming. So, as Tiak says, I'm a professor at Stanford and also co-founder of SambaNova Systems, and we're glad to have SambaNova Systems partnering with Purdue and the PurPL lab with Tiak and co, and we're looking forward to great things. So, as it was said, I'm an architect, right? That's my training. That's what I focused most of my life on, and that means designing computer architectures and sometimes even dabbling in silicon chips and building systems. And so I care about performance, right? So the question is, what is a guy who cares about performance doing at a PL conference? And why did I, get involved in PL? Well, part of the reason I got involved in PL because I thought that, when I was in school, compilers are all about, programming high-level languages, and a lot of the compiler effort was sort of focused on improving the performance of your program, right? And it felt to me around sort of like 10, 15 years ago that the core focus of PL around performance had kind of gone at least from the research angle. Nobody was really interested in performance. They're interested in other things. Not that these other things weren't important, but they just weren't important to me, right? Because I was focused on performance, and so I felt that I needed to jump in and kind of dabble in PL. And I call myself a dabbler because I really don't know what I'm doing. But I felt that there were some things that programming language and compiler technology could bring to the table that could really help performance, especially for the sorts of computer architectures and that I was interested in. So I'm going to tell you a little bit about, what we've been doing at Stanford and how these things all come together. But first of all, a little background, some of which, of course, you already know. There are kind of two big trends in the world today. One, Moore's law is slowing down, right? So whatever anybody tells you, that's the truth of the matter. The time between process nodes is lengthening beyond 18 months and stretching beyond 2 years. And more importantly, the cost of each transistor is going up, right? So Moore's law always said, the cost would come down. Well, the cost is going up. And so what this means, of course, is that the conventional the other thing, of course, that's happening is that we're in a power crisis, right? So we can't afford to power all these transistors because the fundamental things that kept the power per transistor declining as we move from one generation to the next have kind of gone away. It's called Dennard scaling. And so what the problem is that we're faced with a situation where in order to get more performance, we've got to burn more power, and so the inefficient ways that we've been building computer architecture for a long time are completely running out of steam. So the other big trend, of course, is the success of machine learning, right? So I don't need to belabor that point. Eric's told you about it. Everybody is aware of it. And of course, there is this interaction between computer performance and the rise of machine learning. The reason that we have machine learning as being more accurate at doing things like recognizing images and translating languages, why these machine learning neural network-based techniques are better is because of computation, right? Because more computation allows you to ingest bigger data sets and build these more complex models that have higher accuracy than conventional hand-rolled techniques, right? So a notion is that more compute gives you that capability. And of course, this idea has been called software 2.0, right? And Andrej Karpathy kind of coined this term. We have other terms, but this is a much catchier term than I could have come up with. And so we all know that we replace hand-rolled code by code that gets generated by learning from data, right? So the other issue, of course, is power, right? As I said, Moore's law is slowing down, and so, I'm not going to show you very many equations. This is one I'll show you, which is kind of relates power to performance, right? And so what it says that, we know the amount of power this, of course, be more efficient in the way that we do those operations by decreasing the amount of energy per operation, right? And so the way to do that is to be more specialized, right? Because that's the way you get more efficiency. And however, how do you get this more efficiency while still retaining the programmability that you need to implement new and more interesting algorithms, especially machine learning algorithms. So in this post-Moore's law era, right? So what we want to do is improve the velocity with which we can exploit software 2.0, right? All the great things that Eric wants to do with machine learning have to be powered by more computation, right? And that's the only way that we're going to get there, and to be able to, learn the world, right? And so we need greater performance. We need to do this much more efficiently because of the power constraints, and we need to do it while still retaining the flexibility, right? So ideally what we'd like is the efficiency of building a custom ASIC for every program that you want to run, but with the generality of a processor that, of course, can be adapted to any program that you want to run. And so the solution is a full stack approach, right? So you can't solve the problem at any one particular layer in the stack. You need a vertically integrated solution that looks at algorithms, innovation in machine learning algorithms, domain-specific languages and compilers, and domain-specific architectures, right? And so, the interesting thing about this, of course, to this audience especially, is the domain-specific languages and compilers. But of course, compilers are critical all the way down, right? Because you can't, the problem, of course, and we've seen it over the years multiple times, is that some bright young architect comes up with a brilliant idea, and they say, here's the hardware, and it can do wonderful things, and now there's no software, right? There's no way of programming this architecture, so there's no real way of unlocking the wonderful things. So key to new architectures is the right kind of compilers, and of course, as we'll see, it's not about designing the right kind of compilers, it's also designing the sort of architecture that can be compiled to. That's an important aspect. So first, algorithms, right? So the biggest trend, of course, in machine learning algorithms is the increasing complexity of these models, right? So this is some data taken from a talk that Bill Daly gave at SysML, in which he shows the increasing size of models for different types of tasks, and the amount of computation required to train these models. Then the complexity keeps on going up. 100 exaflops for this neural translation model. New models, BERT, requires even more computation. And the models just keep on getting more complex because, of course, you want higher accuracy, right? You talk to any machine learning expert, and they're not really concerned about how much computation is required. All they want is higher accuracy, right? And so if you give them a model, or you give them a way of getting higher accuracy, that's important. So the other trend, of course, is that if you increase the size of these models, complexity of models, you increase the number of parameters, and what you'd like to do is to see whether you can have some sparsity to reduce the number of parameters you need. And of course, while you have sparse connections, you still want to keep your accuracy, right? So both taking a model and then sparsifying it is, of course, of great interest to reduce the number of parameters you need while doing inference. But also, more interesting would be, could you actually train a model and keep it sparse, right? And so that's some interesting work being done there, and lots of interest in that. The other thing that's is happening in the machine learning model space is the use of graph neural networks, right? So the idea is, instead of operating on these matrices, can you do convolutional graphs and build models that represent people, places, and things, and social networks and physical networks, in order to better model the world and better provide more accurate predictions. And so graph neural networks is one example of an exciting area of development in neural networks. Then lastly, the interest in sparsity is an area that is getting lots of interest, because of course if you can compute with numbers that increase in lower precision, I should say, if you can compute with less precision, then of course you can do things with less energy, and I said energy is very important, and also means of course that you can do more parallel computation in a single instruction. And so there are lots of interesting ways of reducing precision. One algorithm that we've recently worked on is called high accuracy, low precision, which is a way of doing training with less than 16 bits in many cases. And the way that you do it is by having some outer loop that keeps track of the precision that you need at every step and uses your fixed number of bits most effectively. So one of the things that really attracts me from a computer architecture point of view to machine learning is the fact that, unlike conventional processing where you are executing things in a deterministic manner and that everything has to be completely correct, the underpinnings of machine learning are these probabilistic algorithms, right? And this is something I learned from one of Eric's papers, right? He put it very succinctly. And the notion is that you only have to be statistically correct. And so what I tell computer architects when thinking about machine learning is relax. Machine learning, and that means you can cut lots of corners and still get the right result, where what the right result means some model that accurately predicts what you want it to predict, right? So you can relax precision. I just gave you an example of that, where you can compute your training or your inference with less precision, and you can get the right result. You can relax synchronization. This is something that traditional parallel programming people just aghast at, right? You want to access shared data without synchronization? It's verboten. You shouldn't do it. But it turns out that you can, right? You can let races happen all day long when doing stochastic gradient descent in parallel, and you still get the right result. And what's more, you can prove it for convex functions, right? You said because the algorithm's fundamentally noisy. It's got some noise floor. You can prove that you can. By having these races, you introduce noise, but the noise doesn't rise above the noise floor, and so the result you will get converges to the right answer at roughly the same rate. You can have fundamentally incoherent memory, right? You can have, anybody who knows about designing architectures knows that one of the most complex parts of a computer architecture is a parallel computer architecture, or shared memory parallel computer architecture, is how you keep the caches coherent, right? Lots of energy gets spent designing those protocols, verifying those protocols, and making sure that they are absolutely right. And turns out that we showed that you could throw away 90% of the invalidates, and you still get the right answer, right? So who cares about coherence? Well, if you're computing your bank accounts, balance, maybe you care about it. But if you are training a machine learning model, maybe you don't care about it. Okay? You can relax communication, right? So if you're sending gradients around, if they're not big enough, then don't send them, right? So it turns out, again, you can get benefits. And this whole idea is about statistical efficiency, which is how fast that loss function decreases, how many iterations it takes, and then hardware efficiency, what each of those iterations takes to execute in time. And of course, the product of the two is what you care about. And the key to all of these ideas, these relaxation ideas, is you can dramatically improve hardware efficiency with very little degradation in statistical efficiency. Okay, so new ideas in machine learning algorithms, and of course you want them to be able to be expressed easily. So here's the idea: domain-specific languages, right? So you want domain-specific languages as a way of representing the programs in this space. And so everybody's familiar with domain-specific languages. I only do explain to this audience. But I will say that one of the key things that kind of drew that was meant to improve programmer productivity, right? So make it easier for programmers to develop their applications because they had just the right methods and data types that matched their problem. But what we saw in domain-specific languages was this high-level representation that didn't have the horrible constraints that conventional programming languages like C++, C had, right? And so that gave you these high-level abstractions that you could think about converting directly to some optimized implementation. And so not only could you have high productivity for the programmer, but you could also have high performance for the systems implementer. So that was the big attractant. And we started working with Martin Odersky and Tiak back then at EPFL. And we came up with this language called OptiML, which for most of you will probably recognize is basically embedded in Scala. And so this was, an implementation of k-means clustering, fairly straightforward. You just find the clusters by using a group by, and then you, based on those clusters, you find the centroids and use those centroids to discover the new means. Okay, so the nice thing about this is no explicit parallelism. There's no indication about what should happen to the data to make it distributed. You could take this representation with the right sort of compiler technology to make it run in GPU and clusters, right? And so the key to all of that, of course, one thing I should note is that you could do the same thing much later in TensorFlow. First of all, of course, you see more lines of code and this explicit representation of the graph as opposed to implicitly. But it's Python, I know. I mean, so one of the other things Yann LeCun said is he doesn't think that the machine learning community is going to move away from Python. And so, as much as I would like to see it, embrace something more interesting, maybe Tiak will bail us out, right, and make Python into something that is palatable to the PL community. Okay, so the key thing is to be able to, languages are the answer. Then the question became, well, so how many do you need? And if you need many of them, then what you need is a framework to develop them, to make it easier to develop new domain-specific languages. So that's what we came up with. Delight, where you had a bunch of DSLs embedded in Scala, and they used this type directing staging idea, which blew my mind when I first understood how it worked, and Tiak developed that with Martin Odersky and others. And the idea that you could describe these domain-specific language operations, but then the core of the performance optimization really came from implementing these domain-specific operators on top of a core way of expressing parallelism and locality. And that was around the idea of parallel patterns, right? So to all you functional programming fans, which I'm sure there are many out here, right? So your good old functional operators on collections were the core of this idea. It turns out that you can't do everything purely with functional operators. You do need to mutate data every now and then because the world needs mutation. I never understood what monads were about, so that was beyond my level of comprehension. So you want something that actually mutates data, and so you do that with some other operators. But here is the representation of that k-means example in a parallel pattern language. Of course, it's just another Scala variant, and which means you can both use it as intermediate representation, but also as something that you can program directly in, because every intermediate representation that can be made into its own language. And the thing to notice here is, of course, these things are nested, right? So it's just not map reduce, right? But you've got a nested set of operators. And you can, write almost anything that you want to do in the data analytics world using this kind of representation. So be it SQL, matrix and linear algebra, relational algebra, you can do all these sorts of things using this high-level parallel pattern language. And then you can do optimizations based on that, right? So you can optimize locality, so you can do tiling, you can do fusing, and you can do all of these things for representations where you can't do the analysis using polyhedral analysis because you've got things that are non-affine. The other thing you'd like to do, of course, is to explore the parallelism landscape or the parallelism space of your application, right? So you'd like to expose as much parallelism as possible to the hardware. You might want to do overlapping of outer loop parallelism and inner loop parallelism, something we call meta pipelining. You might want to overlap memory access with computation, and you can do all of these sorts of things with a high-level compiler that focuses on optimizing this parallel pattern representation. So here's an example of some of the things that we did. So we're working with a group at a chemical biologist who came up with this idea of folding at home called Vijay Pandey. And he's looking at protein folding. So you have unfolded protein on the left going to a folded protein on the right. Turns out there are lots of trajectories. The protein doesn't just fold using a single path, but there are multiple paths. And the way to analyze this is with a machine learning model called the Markov state model, right? So they wrote some Python for that, and it was damn slow. So they went to a hotshot computer scientist and said, well, take this slow code and make it faster. So of course, what she did was she took the code, converted it to C++, because we know that's going to run a lot faster, and used some SIMD intrinsic, some intrinsic x86 code, and by doing that, she was able to speed it up by 1,500 times. Well, and she graduated, and of course she went to get a job at Google, or maybe she went to Facebook, but whatever. She left the group with this code that they couldn't understand. And so what we did was we said, well, we're going to take your Python code and pretty trivially convert it to optimal code, and then we could take that optimal code and we could run it as efficiently on the x86 processor, but we could then take that same code without changing it, run it through the compiler, and generate CUDA that could run effectively on the GPU and give you another kind of 2 to 3x speed up, right? So that was the idea, is that you could take these high-level DSL representations and through compiler technology and optimization, get them to run effectively on a full range of instruction set driven processes. But if I go back to my opening introduction, I said, well, going forward, instruction set driven processes, the conventional ones, are not going to be efficient enough to keep the performance improvements going in the face of the slowdown of Moore's law. So what do we need then? We need something that actually is more specialized, more domain specific, that can be more energy efficient and can give us more performance in a constrained power environment. So let's talk about domain specific architectures. So if we look at sort of where we are today, we've got CPUs. Of course, lots of CPUs get used for machine learning and both inference, for both training and inference, and they've got lots of threads, right? So they, if I go back in time to the mid-90s when I was saying the future is multiple threads and everybody thought I was crazy, well, now, of course, turns out we weren't so crazy. And so, of course, we've also got SIMD. GPUs have massive numbers of threads. Also make use of vectors in SIMD and high bandwidth memory. A TPU, to a TPU, right? If the hammer is matrix multiply, then everything has to look like a matrix multiply nail. And so, TPU1 was one big ass matrix multiplier, turned out to be too big. So TPU2 was two medium-sized ass multipliers, and who knows what 3 and 4 will be. But that's I should say dense matrix multiply, right? And so, of course, that is a fundamental limitation in what you can do with a TPU. And so the question is, what should be next, right? So if I look into my crystal ball of ML algorithms, I'll find out that it's unclear what's next, right? Because, if you look at the machine learning field, you've seen these graphs where the number of papers on arXiv for machine learning is growing faster than Moore's law. Well, Moore's law is slowing down. So clearly, we're going to see a divergence between the number of ideas that get generated and the number and our ability to implement those directly in hardware, right? So forget this notion of, I'm going to figure out what the right algorithm is, and I'm going to encode it very efficiently into some ASIC, right? And I'm going to make it run really efficiently. Well, the problem is, of course, is that it takes you 18 months to 2 years to do any hardware, and by the time you come up with your hardware, the algorithm has moved on, right? And the one that you accelerated is no longer important. But what seems to be clear is that, from looking at the algorithms, there's a couple of things that you want. I mean, we really think that this hierarchical parallel pattern data flow model is something that seems pretty fundamental to a range of applications, not just machine learning. And so that's a natural programming model. So kind of accelerate something like that seems to be something that would be good. Then there's importance of being able to dynamically change your precision to support algorithms like high accuracy, low precision. Sparsity is important, right? So just doing dense matrix operations isn't going to be something that will be general, and you want to find a way of implementing algorithms that are sparse in an efficient manner. And then flexible mapping, right? So if you look at a graph of machine learning operators, there are many ways to actually map those operators into execution. You can do one operator at a time in a data parallel fashion. You can do multiple operators at a time laid out somewhat spatially in a model parallelism implementation. You could do something in between, right, that kind of combines data parallelism and model parallelism. And there's sort of just many ways to skin the machine learning model execution cat. And so, you need to have the ability to do flexible mapping, all right? So the other thing that I want to bring up is what I think is a current bottleneck to a lot of architectures, right? Which is this this need to go through this narrow path through an instruction set, right? So if you think about programming model, interface, and hardware, right? So the interface is the instruction set architecture, and in the general purpose world today, it's x86 on the server and on ARM in the mobile device, but they all kind of lead to the CPU implementation architecture. And then you've got, in the GPU world, which of course is where most of the machine learning training takes place. You start with CUDA. You've got this PTX as the instruction set architecture, and then GPU as the hardware. And so, the problem with ISAs is you've got a fixed set of operations, that kind of limits what you can do. And if you want anything else, you've got to put those operations together. They tend to be low level, and they tend to be inefficient because you've got to do all this decoding, and you've got this fixed set of resources that the instructions touch. But if you start from this hierarchical parallel pattern model, then what you tend to naturally get is what we call hierarchical pipeline data flow. And that gives you a wider interface because it allows you to express the operations at a higher level. And so the way that we came up with for describing this hierarchical pipeline data flow is through another embedded Scala DSL that we called Spatial, right? So Spatial is a language for describing hierarchical pipeline data flow, and it's both an IR and, of course, a language also. And it expresses these parallel patterns as pipeline data paths. It has an explicit memory hierarchy, right? So you say explicitly where data goes. So it's not for every programmer, but performance programmers like to manage their memory because that's how they get a lot of performance. And so we give you a way of doing that. It's got hierarchical control, explicit parameters so that you can explore the design space. It's got a bunch of storage templates. I'm not going to spend too much time here. Let me show you an example. Hey, dot product, right? The core of all machine learning, right? Dot product. So it's just a zip and a reduce, right? I can't see, yeah. And for all you functional programming people, I don't need to explain that. But it turns out if you want it to run it efficiently, you've got to tile it, right? So it turns out to be a two-level reduce. And this is how you'd explain it, how you'd describe it in Spatial. You put the vectors explicitly in memory, so in DRAM. Vector A and vector B in DRAM, and then you would put your tiles TA and TB in SRAM, right? And then you have explicit loads from a piece of the vector A into tile A, a piece of the vector B into tile B, and then the two-level reduce, the reduction of within the tiles and then the reductions across the tiles. And that's it, right? And so you might get some hardware that looks like this if you translated that directly into hardware. However, of course, that would not necessarily be what you want if you wanted a different kind of algorithm, say convolution. So how about an algorithm that, one thing that you might want to do is explore the different parameters. So tile size, how much overlap you had between memory fetch and computation, how much pipelining and parallelism you did in the core reduction computation. So all these parameters could be explored by a compiler like Spatial. Okay? So now the question is sort of what if you wanted some flexible way of implementing that Spatial program? So that was the idea of the Plasticine architecture. So initially what we did was we said, well, this would be a great way to describe FPGA sorts of designs. And we tried designing FPGAs using Spatial. And it was pretty successful. However, we found out that FPGAs have a number of fundamental problems. They've got a limited clock frequency that they can achieve. They've got lots of overhead for the reconfiguration. And so the question is, could we come up with something that would be a good target for Spatial, but would be much more efficient than an FPGA? And what we came up with is an architecture that we call Plasticine. And Plasticine, for those of you who didn't grow up in Europe, is a children's modeling clay. Okay? And children's modeling clay that is oil-based. And the nice thing about that is it never hardens. So people say, why didn't you call it Play-Doh? Well, we didn't call it Play-Doh because if anybody who's played with Play-Doh knows that if you leave Play-Doh out, it hardens. Plasticine does not harden, and so hence the name, because it's always flexible. And it's designed to execute the Spatial programs very efficiently, and it's about 100x in performance and performance per watt compared to a commensurate technology FPGA. So the core of the Plasticine architecture, which we're calling a reconfigurable data flow architecture, because that's essentially what it is. And it has both a pattern compute unit, which is a SIMD pipeline that can execute things very efficiently, and then and it's hierarchical in the sense that you can both do computation within the PCU, and of course, if you need computation in the out or can fit within a single PCU, and you use the connectivity to other PCUs to build more functionality. And then the pattern memory unit, and the key thing about the pattern memory unit is the ability to do an old architectural idea called decoupled access execute, right? So you can have this engine that fetches and stores data and have that independent from the execute unit, and it gives you a lot of efficiency. And so the pattern memory unit has the ability to support different kinds of memory access, has the ability to support banking and buffering, and that is important if you want to allow parallel execution. Okay. So then the question is, why is Plasticine better than an FPGA? Well, the key thing is that it has this coarse-grained compute tile. Tiles which are composed of pattern compute units and pattern memory units. This wide interconnect, and which gives you very efficient connectivity between the coarse-grained compute tiles, and this gives you overall better scalability, a much higher clock rate, higher logic density, and most importantly, much less reconfiguration overhead, right? So you can basically use your silicon much more efficiently than you could with an FPGA. So the key thing then, of course, is actually compiling spatial to Plasticine. How much time do I have? 10 minutes. Okay, good. So what you want to do is to be able to take the representation of spatial and convert it to something that executes very efficiently on Plasticine. Okay? And you'd like to do this for a wide range of applications, enable the kinds of loop optimizations that are required to get high performance. It turns out there's basically 4 steps to doing this. First of all, you want to optimize the way that the way that you do parallelism and pipelining. So how much parallelism are you going to exploit in the spatial program, and how are you going to pipeline? You want to be able to convert the loop constructs to Dataflow. Dataflow is very efficient in execution, but of course it's not a very easy programming model. And then you want to partition your computation so that it fits on your architecture, and then finally do place and route. And so, if you start with your representation of your program as a set of nested loop controllers, and then you've got pipelining. You can do pipelining within the body and parallelism across the loops. You can convert the loop level computation to Dataflow execution. And the way that you need to do this is you need to distribute the control, right? So you think of sequential control as following this single thread of control. That won't work very well in a Dataflow environment. What you need to do is distribute the control, and that means that you've got to duplicate the control across your different compute units, and you're going to do that by allowing them to independently follow the control paths by distributing the control. And of course, then they are sending data from one compute unit to the next. And of course, because you've duplicated the control, the sender sends data and the receiver knows how much data is going to arrive, and you don't have any overall central control synchronizing things. And this gives you a way of scaling the design across the chip and potentially even between chips. So it turns out that once you've got some representation that matches your your spatial program, you might turn out that the amount of computation that you have in your particular execution block, or the amount of memory that's required, exceeds what you have in your physical components, in your PCUs and your PMUs. And so you have to do graph partitioning, right? And so the idea is you partition your graph so that things fit. And the key thing about doing this graph partitioning is you can't introduce any extra cycles, right? So the top path shows how you partition so that no cycles are introduced, and the bottom path is one that introduces cycles. And of course, if you introduce cycles, given this distributed control, what you'll get is deadlock, right? So the program will not work correctly. So it's vitally important that you compile correctly, because if you don't compile correctly, you end up with a program that deadlocks, and that's no good. And then lastly, you do place and route, right? So you know, the unfortunate part about having a spatial architecture is that you have to spatially position the computation in memory. So finally, you do need to do some sort of place and route, and that's the last step that's required in the conversion of your spatial program into your something that will match the Plasticine architecture. So the key thing about actually doing the place and route is making use of the, making use of the links between the computational and memory units effectively. Turns out that in Plasticine we've got a level, you are using the links in a very high bandwidth fashion, right? Because you're moving data every cycle from one operator to the next. And if you want to do that efficiently, then you want to lay out the computation statically. However, not all of the, you don't have all the knowledge to do things statically, and you may, when you lay the computation out statically, that means you're dedicating those links in your hardware to particular paths in the program. And so it turns out that maybe you run out of those links, and then it'll be very difficult to map your program. However, if you've got some ability to have dynamic networking, then you can use the cases that potentially don't have very high bandwidth demands, but are required for correct operation of the program. You can use those dynamic links, and then you are able to map your program. So the idea is high bandwidth links go to the static network, and lower bandwidth links that are required, of course, for the correct operation of the program go to the dynamic network, and turns out to work very well. So overall then, you are, again, to kind of recap, you're starting with a domain-specific language. These days it's Python or TensorFlow. We'd rather it be some embedded embedded Scala DSL, but you can't always have what you wish for or what you did research on. But we influenced the world, right? So TensorFlow and PyTorch have taken the ideas and come up with something that roughly good enough, and we can extract a computation graph. We can do all the kinds of operations and optimizations on that computation graph, express as parallel patterns, and we can optimize the locality, we can optimize the parallelism, we can generate spatial, and then we can convert the spatial to something that can be efficient running on a Plasticine style architecture, which is a spatial architecture composed of memory and compute units that can be configured, right? And so what we have then is a mapping, just showing you mapping from the dot product to Plasticine. More interesting example here is logistic regression, right? So the thing to know is that you've got the compute units in blue, the memory units in green, and the address generators for off-chip access in orange. And what you see is you see varied communication between the different components, right? You see fan out, see fan out, you see fan in, you see nearest neighbor connections. There's all sorts of communication going on that has to be effectively supported by the on-chip interconnection network in order to get very high performance. And as an example of RNN serving, this is a paper we presented at SysML this year, shows the advantage of kind of doing things at the parallel pattern level as opposed to the BLAS kernel level, and that you can kind of do more optimized fusion than you could if you just you come in at BLAS level 2. And then because you have this configurable hardware that can be reapportioned to match the kind of application that you're running, you can actually use the hardware more effectively. And so in this example, given the same rough amount of compute with different size LSTMs and GRUs, you can see a much higher fraction of the compute being used with a Plasticine architecture compared with something like a V100 or even a Stratix FPGA. So the point here is it's not about raw compute, or it's not just about raw compute. It is also about the efficiency with which you can use that compute, right? And so if someone says, I've got 200 teraflops, but I only get a small percentage of that on real applications, then you would rather have the architecture that gives you 100 teraflops and gives you 90% of that most of the time. And so that's the point, that not only is it an architecture, Plasticine is an architecture that has a potential for a very high peak, but because of the flexibility that's inherent in both the underlying architecture and the compiler stack that targets the architecture, you can get very high fractions of that peak. So to conclude then, we can have it all, right? And having it all means having all the P's: high productivity, programmability, power efficiency, high performance, and portability. And the way to do it, of course, is using the stack that I've outlined, new ML algorithms that exploit all the niceties of the fact that you're doing this stochastic computation, high performance DSLs that give you not only high productivity for the programmer, but also the ability to translate those abstractions efficiently using a high level compiler into something that represents spatial pipelines. And spatial pipelines can then be converted using low-level compiler techniques into new domain-specific architectures like Plasticine, which are fundamentally going to be more efficient at using silicon. And the whole goal, of course, is to move this whole Software 2.0 field forward by providing the sorts of computation that's required to keep those more complex models and there's more data being processed to get greater accuracy on all the things that we want. So with that, I'll end.
We have time for a few questions, so please speak into the mic so that we can have the whole conversation recorded.
Very nice talk.
Thank you.
Very nice talk. No.
I can hear you.
Okay, so it's only recording, so it will not amplify your voice.
Very nice talk.
Thanks, Phil.
I think I misunderstood something fundamental, because at one point you were talking about taking spatial and doing things like fusion on spatial, but I thought you would do that at the higher level, like at OptiML or Delight.
You do it on both levels. You can, so there's no confusion. Sometimes we write things with optimal and delight, And sometimes we write things directly in spatial, right? Because there are, programmers who are more focused on thinking about architecture things, and they want to start in spatial. And so they need to do fusion at that level too.
You have to redo your diagram then.
No, it just means you can come in at any level, right? There's a path that goes all the way from delight all the way through spatial, and then some architects, right, say, screw it, I don't care about starting at the high level. I want to experiment and do some things at the spatial level down, and so then you need to do some fusion there.
So very nice talk. Thank you.
Thanks.
Basically, I think your talk is about focusing on the application of machine learning, but from my understanding, the machine learning is not the only data parallel applications you have in this world. You have something like MapReduce and other data parallel applications there as well. I know the engineering specifications and the constraints will be different for these other applications. But do you think that similar designing principles and ideas could be used to improve engineering in these applications as well?
I think I'm missing something. So we handle MapReduce and sorts of applications.
So basically, what I'm thinking about is that you're trying to compile the spatial II onto some specific hardware that works on like a GPU or a TPU, something like that, right?
Yeah, yeah.
So basically, what I'm talking about is that if you have a larger data set, like in MapReduce that is used in the industry, they have larger data set that need a lot of more kind of storage for this.
Yeah. So you could start with a Spark-like application that represents computation on large amounts of data, and you would do all the sorts of analysis you need at the high level. And in fact, if you looked at the earlier Delight work that we did, we started with those kinds of representations, right? And so all it means is you need optimization at every level, right? You need optimization at the cluster level, but you also need optimization down at the components that are actually doing the execution, right? And one of the dirty little secrets, as anybody will tell you, is that Spark was, of course, a much more efficient implementation of MapReduce, but even Spark without a compiler optimization is pretty inefficient, right? And so if you can, on a single node, do your computation efficiently such that you could completely, if you haven't had enough memory on a single node, you wouldn't necessarily want to use Spark because it'd be very inefficient. So the only reason you use Spark is because your data won't fit on a single node. But still, you want to make sure that when you're executing on a single node, you can do it as efficiently as possible. So I suppose what I would say is you still need the full set of optimizations across the computation, both across nodes and within the node. And all I'm saying is that you want to be able to do that effectively. Even for large training problems, right? You've got a cluster of GPUs and that are connected by a network, and you want the efficiency within the GPU node, and of course you want efficient communication across the nodes.
That probably answers my question. Thank you.
Yeah.